right, morning everybody. Let's go ahead and get started. So today we're going to move on, talk about solving really easy exponential equations. It's nothing complicated at all. Of course, we're going to practice the other easy stuff, graphing exponential functions. So let's go ahead and do that today. For each of these functions, draw a rough sketch of its graph, identify its domain, range, y-intercept, horizontal asymptote, and end behavior. So all the basic stuff that we've been practicing all year long. Here we go. Number one says -7 to the x. Now you have to know PEMDAS, of course, to survive anything. What do you do first, exponents or multiply? Exponents, right. So this is the exponential right here, 7 to the x. The negative in front is what happens to any graph we put a negative in front. That's a vertical reflection kind of thing. So if you know a graph of 7 to the x looks like, all you got to do is flip it and you're done. 7 to the x, if the base is more than 1, you can expect this to kind of be your template right here, okay? Goes up and increases forever just like that. So if it's -7 to the x, then it's going to open downwards like that. Key points on the regular graph to consider: there is a horizontal asymptote here, and it does go through the y-axis at 1, because anything to the 0 power is 1. So based on that information, we can just flip it over. What would that look like if I flipped it over? Well, it wouldn't be at 1. It'd be down here at -1. The horizontal asymptote would be y equals 0. They're still going to level off to there. If you flip something over the x-axis itself is still the x-axis. And that's just going to kind of open downwards like this. So exponential opening down like that. And that's pretty much it. That's a good rough sketch. Domain, obvious as heck. It exists everywhere. So duh, -infinity to infinity. Range, obviously, it goes down from -infinity up to 0, but never actually touches it. That's what an asymptote is. Never actually touches it. So you want to go from -infinity up to 0 with a parenthesis on this one. And let's see, what else we got? Y-intercept. Well, there it is. We already labeled it. The y-intercept is at -1. Things they ask us for: domain, range, y-intercept, horizontal asymptote, end behavior. Well, what happens on the ends? Let's see about that. Limit as x goes to -infinity. That just means to the left. Obviously, the graph just levels off to 0 as you go to the left. And as you go to the right, this thing just keeps on going down. So it goes down to -infinity. And that's really all there is to that one right there. Got a graph flipped over the axis. Got yourselves the asymptote and the domain and the range. Okay. Let's move right along. Number 2 is stating the function is -1/2 in front. And then you have a 1/4 to the x. There's the exponential right there. And then a +6. So let's see what we can do with this thing. Well, let's see. First off, the base is less than 1. Would you concur? So this isn't one that goes up. This is one that goes down. So in my mind, 1/4 to the x kind of looks like that, something that's going down like that. Of course, we don't have just 1/4 to the x. There's also a negative something in front. What's the negative do? It's going to do the same thing. It's going to reflect it. So it's going to go down like this. And what's the +6 going to do? It's going to scoot up 6, right? Now, normally, this would level off at 0. Would you concur? So if I move it up 6, where's it going to level off now? 6. Yeah, makes sense. 1, 2, 3, 4, 5, 6. I like to start with the horizontal asymptote. Because that's kind of like, oh, it's going to hug this thing. It's going to get close to it. So I kind of have a feel for that right there. Now, where's it going to cross the y-axis? You know, this was a stretch, too, this half, right? This half stretches things. If you're not exactly sure where to put the y-intercept, just go with what a y-intercept is. Anywhere on the y-axis, x is 0, right? If you plug 0 in, what's anything to the 0 power? 1, right? 1 times -1/2 is -1/2. And -1/2 plus 6 is what, like 5.5, something like that? So up here about 5.5 is where it's going to cross. Right there, it's going to cross at 5.5. There's our y-intercept. There's nothing. And like we said, it is going to be a reflection. So it's going to kind of open like this-ish. So maybe something like that right there. That's probably a good sketch of this thing. Any questions over the setup or the logic so far? All right, and then the last one today, same kind of stuff, just graphing exponentials. Of course, we didn't really analyze this one. What's the end behavior? We should say the end behavior of this one before we go on. What happens if you go to x goes to negative infinity? It goes down to negative infinity, right? And as x goes to infinity, levels off to 6, right? On the right side, it levels off to 6. So there's our end behavior. And the domain, of course, would be negative infinity to infinity, and the range would be everything from negative infinity up to 6. And same idea on the third one. Third one has a -2 in front of this exponential right here. And then it's got a -2 on the end, which we all know moves things down 2. So right off the bat, things are moved down 2 without even putting any thought into it. That means this thing's going to level off somehow down at y equals -2. That shift always moves it down. All these ones, the ones that increase or decrease by default, level off to 0. So if you just look at the shift up and then in the end, you can move it up and down. All right, what's up with the rest of this nonsense? Well, it's a base more than 1, correct? So I'm thinking it grows, but then there's a negative in front, so that's going to reflect it, correct? So it's going, instead of growing like this, I'm going to reflect it and kind of have it go like that-ish. So there's kind of a rough sketch of what this thing would look like. Try to get this over with. Where in the world does it cross? Where's the y-intercept? Well, again, x is 0 on the y-axis. So if you plug in 0 for x, this exponent will be 1. That'd be 2 the first, or 2. 2 times -2 is -4. And -4 minus 6, or -2, excuse me, is -6. So way down there at -6 where it's going to cross. Domain's a normal thing, negative infinity to infinity. Domain, negative infinity to infinity. Range, obviously, it goes down from negative infinity up to this line, which is at -2. So negative infinity up to -2. And then the end behavior is pretty obvious, too, from looking at the graph. As you go to the left, this thing levels off to -2. And as you go to the right, this thing just goes down forever. So it goes down to negative infinity right there. So we got all things. Pretty easy when you got a picture in front of you. All you got to do is read it off and understand what the basic definitions are that we've had for many years of our lives. Okay, let's go ahead and do LGs now. Here we go. Solve basic exponential equations today. Solving basic exponential equations. To do really hard, well, average difficulty, we need logarithms, which will be the next topic. Yes. Yes. So before they actually get to the real things that solve exponential equations in the next chapter, they're going to give you some little baby stuff today about solving easy exponential equations. Nice thing about exponentials and logs, which come for the next thing, is that inequalities you do the exact same way as you do as equations. It's very easy. So if you can solve an equation, you can solve an inequality. It's simple. Homework due today, 7.1, I believe. We're in unit 7, I think. Oh, yeah, okay. So that's due. Get that turned in. You could do it on paper or you could do it online. Either one's okay. And with the new stuff comes a new homework, and here it is. Homework 7.2 down below. Take a minute and jot down what problems you need to do. I would encourage you to do this one on paper. The more you do on paper, the better it is for you. Very strong correlation between those who do it on paper and those who do well on tests. Very strong correlation. 1 through 6 all, 15 through 40, just the multiples of 5. So just doing every 5. That's all you got to do with it. Do it on 2 days. Wednesday, we're back to normal schedule. We've made up everything from snow days and ACTs and things like that. So we're back to our normal rhythm. Lecture, workday, things like that. So how we do on Wednesday? Let's get going. We are doing section 7.2 today. Let's take a look at what it is. It's about solving exponential equations and inequalities. Found on page 365 of your book. And your problems, of course, would be not too far after that. All right, here we go. Let's get started. Section 7.2. Let's do it. Okay, so an exponential equation is just what it sounds like. It's an equation. So you're trying to solve something. You only try to solve things when there's an equal sign, by the way. You don't, seems to be some confusion about that. But this is what you want to do. Please write down this middle part right here. If these are the same, see how they got the same base? They both got a base of b right there. Then if their bases are the same, then their exponents are the same. That's my main theme for the day. Write that down in your own words somehow, however you want. If you can get the bases to be the same, then their exponents must be the same. So if you had 2 to the x equals 2 to the 4, well, they both got the same exponents. That would mean x equals 4. If you had 7 to the 5th equals 7 to the x, well, then 5 equals x. That's the main theme of today. And down below are some good kind of summary of all the steps you'll need to do in order to get through this particular section. You would like to work with bases that are not, I'm trying to like make one rule that'll cover everything for you. If the bases are less than 1, replace them with their reciprocals raised to the negative first power. You can always take any fraction and flip it as long as you raise it to the negative first power. That's what a negative first power means. It means you move it from the top to the bottom or the bottom to the top, things like that. In this particular section, since it's the easy stuff, get the bases to be the same, and it will be possible. Every single one in your homework, it will be possible in this unit. Of course, not in the real world. It's not going to always work out nicely for you, but here it will. And at the very bottom, if the bases are the same and greater than 1, you only need to consider the exponents, which is what I was kind of saying before. If the bases are the same, you don't need to worry about them. You just worry about the exponents. So b to the x equals b to the y. Well, those bases are the same. That means x equals y. That's your main theme for this. That's really it. Besides knowing some basic exponent rules from middle school and things like that, it really isn't going to be that complicated. So we'll see if we know that. One of the reasons I want you to have the bases less than 1 is just because when we do the inequalities later on, these same exact rules will cover both cases. So you don't have to get the bases to be more than 1 if you're doing an equation. But I'm just trying to make one blanket rule so we don't confuse ourselves with 2 rules. Seems to get us. All right. Let's see what kind of things they're talking about. What the heck do they mean by this? Well, here's your first particular problem. Well, let's do this one first. Here we go. Jot this down. 4 to the 5x plus 1 equals 64 to the 7th. These are both exponentials. They have bases and things in the exponents. Okay. The first one on the left, of course, is the main exponential because the variables are up in there. 5x plus 1. So here's all you got to do. Step 1. Are there bases less than 1? 4 is not less than 1, right? 64 is not less than 1, so that's checked off. What's the second thing in your list they'll say to do? What should you do with the second thing? Get the bases the same. These bases are not the same, are they? But look at the numbers they're giving you. These should ring a bell because you just got done with the unit about things raised to powers and stuff like that. You should always think maybe I can write these bases somehow the same way. Now you can write 64 in terms of 4s. Does anybody know how to write 64 as 4 raised to a power? 4 raised to something is 64. Does anybody know? Yeah, it is. Very good. So that's exactly what you're going to do. You're going to call this 4 to the 3rd, and that's raised to the 7th. And they're always going to give you numbers like this where it's 4 and 64, 27s and 3s. They're always going to give you things that work out like that. Now here's the only thing you have to remember from middle school exponent rules. What do you do when you have a power raised to another power? Anybody know what you do with your exponents when you have a power raised to a power? No, you don't. You multiply them if you have a power raised to a power. So make sure you write that down. If you didn't know that rule, write that down because you're going to need that all the dang time on this stupid stuff. In fact, as a general rule, if you have something that raised to a power and raised to another power, you multiply their exponents. You are going to use that one a lot. And if you're not using it, you're not doing it right. So then over here on the right, well, then this would be 4 to the 21st. Would you concur? 3 times 7. Wow. So 4 to the 21st. And that's your main job. Your main job is to massage things in that way, somehow, to get the bases exactly the same. Are the bases exactly the same now? Yes, they are. And the theme is, if the bases are exactly the same, then you can basically ignore them, which is something we like to do. We just like to ignore things, which is great. So now this equation is just comparing the exponents. If their bases are the same, their exponents are the same. So this exponent, 5x plus 1, must equal the other exponent, which is 21. This is it. This is all there is today. Anything confusing so far? We're just going to practice the same crap all day long. And after that, then it's just pretty easy. You move the 1 over, divide by the 5, and you get an answer x equals 4. You don't need to check your answers. There's nothing extraneous that's going to happen. No tricks, no weirdness. Okay, you get your answer out, you're done. That's it. So this one, x equals 4. Nothing too bad there, I don't think. All right, let's go back. And there is one equation regarding money that I would like to discuss with you. They like to discuss with you. And it's about compound interest. So please write down this equation here. And let yourself know this is about compound interest. This is a very practical, real-world thing. Even if you don't go into anything that requires any logic or math or things like that, you'd still need this. Can't avoid this. This is how much money you're going to make after a particular investment. And it's very, very important you know what all these letters stand for. So let's define them very, very, very carefully. If you're putting money into something, A, which is on this side, and that's what you get out. It's an equation. You plug things in, you get something out. A stands for the amount of money you have at the end. Amount of money at the end. So the concept is you're putting money into an investment. It's earning interest. It's compounding. That's what compounding means. You get some interest, then you have more money because you have interest, and they take that more money, and then you have interest on that, and interest on that just keeps getting bigger and bigger and bigger, compounding on itself. P is a financial term. It stands for how much you actually started with. It's the word principal. Principal. How much you start with, how much you invest. R is your interest rate. And it's very important you put that in as a decimal. As a decimal. So if they say 5%, 5% is not 5 as a decimal. Anybody know what 5% is as a decimal? 0.05, exactly. Yeah, make sure you put in the right thing. It's a very easy equation to do. You're just plugging things in the equation, putting your calculator. It's very simple. Now, T obviously is time. And that should usually be, unless they say otherwise, you can assume that's in years. So I invested P principal. I invested $10,000. There's my principal. The interest rate is 7%. Great. That's 0.07 for R. I invested it for 20 years. T is 20. The thing that's weird is this end thing, which is how many times per year it compounds. If you actually go out in the real world or something like that, for example, my mortgage payment, I pay it every month. The interest that they charge me on my loan is not just once a year. It's like, oh, here's your annual rate, or if you could buy a credit card, here's your annual rate of 20% or something like that. That doesn't mean that they're going to wait all year at the end of the year charge you 20%. That means along the way, they're going to split this 20% up into every single month or something like that. And that's exactly what this n does. It takes your rate and it divides it by, if you're doing 12 months, if there's 12 months, how many times a year does that happen? 12 times, right? So the rate would be divided by 12. But then there's 12 of them in a year, right? So you're multiplying by 12 as well. So that's kind of the concept right here. Now, I want to make sure you get this buzzwords down. What if they said something happened annually? We should know what that means. How many times a year does that happen? Once. That's a key word that n is 1. They might use the word biannually. That means twice a year, right? Yeah. So that means n equals 2. If they said monthly, well, how many of those are in a year? 12, yeah, so n would be 12. If they happen to say daily, they could compound your interest every day. Then n would be 365. But n stands for how many times per year this happens. And they will flat out tell you that. They might say semi-annually. It's like half of a year or something. That's also n equals 2. They might say quarterly. How many quarters are in a year? 4. Yeah, exactly. Things like that. So just kind of use common sense about what words mean. And that's what n is. It happens that many times per year. After that, you can figure out all those things from the word problem. You just plug it right in this equation and it spits out the answer. It's very, very easy after that. See if we can find an example with that. Yeah, we'll come back to it. Let's do another straight up math problem before we actually apply it. Hang on to that. Tuck it away. It will be used. Let's try this thing. 1/2. Write her down. We'll come back to the money thing. The money thing is cute, but it's very, 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 very easy. We can just like do one example in a minute and then you'll be done because you're just plugging things in your calculator essentially. This is the stuff I'm worried about, the math. Okay, I see a problem right at the bat. One of these bases is less than 1, correct? Okay. So here's what you do. And again, guess I'll make a rule for you again. We'll remind the rules. If you had a fraction, let's say a over b, and it's raised to some power, you can flip the fraction if you make its exponent negative. That's another oldie rule from back in the day. Way back when we first learned exponents, that was something that would follow naturally from the basic rules. So if you have a fraction that's less than 1, the first thing you're going to do is you're going to flip it. But what do you got to do to the exponent when you flip it? You have to make the exponent negative of whatever it was. Okay, that's kind of one quick rule to take all the thought out of it for you. So on this one side over here, up 1/2, that's less than 1. That's no good. So I'm going to flip it. And if you flip 1/2, what do you got? You just got 2, right? But just you got to make sure you follow the rules. If I flip this, I have to make this negative. That means everything. Okay, so negative of all this. That'd be negative 4x plus 16 in this case. Do you agree? Negative of that entire exponent would be this. Questions over that move so far with the rule? Okay, that's an important one too. Now over here we got 16 to the 2x minus 5. I really haven't done anything with this. Well, at least that base isn't less than 1 now. That's good. However, their bases are not the same. Do you agree? Probably you can always take the bigger one and write it in terms of the smaller one. So does anybody know 2 raised to some power is in fact 16? Does anybody know what it is? It's to the 4th. Very good. Yep. So I'm going to rewrite the 16 as 2 to the 4th. And don't forget that the 16 is still raised to the 2x minus 5. And that's what I mean by easy ones today. All these numbers will all be set up so that this will always be able to be done. Now, we're not quite there yet because over here we have some simplifying to do. We have a power raised to another power. And as we said before, when you have a power raised to a power, you multiply your exponent. So this side is going to be 2 raised to the, well, 4 times all this stuff, which would be 8x minus 20. So a lot of preliminary work just to get things set up. But after that, it's cake. Because once you got the bases to be the same, their exponents must be the same. So now I can just say negative 4x plus 16, the exponent on the left, is 8x minus 20, which is the exponent on the right. And you got some stupid little easy, linear thing. You move this over, call it 12x. You move the 20 over, you call it 36. You divide by 12, and you get x equals 3. So a couple of quick two-step equations, beginning algebra 1 stuff. And that's pretty much it from there. Okay, the hard part's going to get to be the bases to be the same. If you can do that, then you're pretty good to go. Questions over that example? All right, let's keep playing. Let's see what else they got to throw at us. Well, here's a money one. Let's actually do a money one now. Okay, we wrote down the equation, so look at that real quick. Here's example 3. We'll see if we can actually apply it to a problem. So again, the equation was A equals P 1 plus R over N to the NT. And if you take a look at the setup, all you got to do is match things up and see what they are. Here we go. We're going to read nice and slowly. Luciana deposits $1,700. Whoop, that's how much you put in. Can you tell me what letter in this equation represents how much you invested originally or how much you put in? P, the principal, exactly. So right off the bat, I'm going to replace the letter P with 1,700 because that's how much I plugged in. The account pays 1.8% annual interest. Okay, that's clearly your R, right? Your interest rate. But don't type 1.8. What's 1.8% as a decimal? Anybody know? It's 0.018, right? If you're not sure, just divide by 100, right? That's another thing to do. It's called percent per 100. Cent means 100. 100 cents in a dollar. 100 legs on a centipede. Things like that. Okay, so there's that. There's R. 1.8% is 0.018. Now it says it's an annual interest rate, compounded monthly, right? Oh, monthly. How many times a year is that happening? 12. What letter represents how many times per year you have something? N, exactly. So you plug in 12 for N. And then up in the exponent, there's N again. We just said that was 12, correct? Times and then T. So how long is she investing in this for? What will be the balance after 5 years? Well, T is 5. So that's it. That's all you got to do. Now you get your calculator out and type it all in. As long as you don't mess up PEMDAS and parentheses, it should be a piece of cake. Type it in just like it looks. I'm getting this number. See if you get this number too. If you get this number, then you're doing things fine. Should be easy points for you on the test when it comes to that. If not, then we're in trouble. Make sure you write to 2 decimal places because it's money. Okay, money, dollars and cents, right? So I should have 2 things after the decimal place. And that's about it. I mean, I don't really want to beat a dead horse because it is that simple. Any questions over this equation? As long as you know what the letters stand for, and you can take them out of the problem and plug them in the equation, it really shouldn't be too tricky. So we got that all figured out now, which is fantastic. Let's see if you guys can just do one on your own. All right, here's another one. Boom, boom. Very similar. Aisha deposits $500 in a checking account, pays 0.9%. Careful with that. Turn that into a decimal. Compounded twice a month. Oh, man. How many times a year would something that happens twice a month happen? I don't know. Anybody know if something happens twice a year, how many times that would happen in a year? Or it should be twice a month, excuse me? That's a dumb question. Yeah, if it's twice a month, well, then there's 12 months in a year, so that happened 24 times in a year. So your N is 24. Bi-weekly, you could say that. And they want to know the account balance, the amount A you'll get out after 25 years. Very, very similar setup. So that should look something like mine on the board. Yours kind of look like that. Same things in the same spots, right? N's 24.009. That's what 0.9% would be. When you type it all in, I'm getting, well, what are you guys getting? Anybody want to venture a guess? 4,000 something. I did not get 4,000. I did not get 1,000. I got something less than that. I got 626, yeah. Might want to be careful with the exponent. If maybe the exponent's throwing you off, you might want to put it in parentheses just to cover your butt. If we're having problems with that, that's probably the first thing I would diagnose. About 13 cents left over, something like that. I would advise you always round your cents down, because banks are never going to give you a fraction of a penny. They're going to steal it, just like in Superman 3. I like to bring that up all the time, but nobody ever knows what I'm talking about, so it's okay. Have you seen Superman 3? Richard Pryor? Yeah, good stuff. Okay. Now, the last thing is inequalities, which is the same thing. Okay. In fact, please do not copy down that box again, because it's the exact same box. I made one box to cover all situations. You're welcome. But it's the same idea. If you have an exponential compared to an exponential greater than another exponential, and their bases are the same, then you can just compare the exponents, okay? So really nothing more to say about this. In fact, if you look at the middle ground right here, it says if b to the x is greater than b to the y, well, their bases are the same. That means x is greater than y. And the same would be true for greater than or equal to, or less than or equal to. These will all work out as long as you first get your bases to be more than 1. Fair enough? Okay, you don't have to do any thought at all. As long as you get your bases more than 1, then this will work for inequalities. It'll work for powers, anything that might in fact happen. So here's a complicated one. Let's take a look at this. That's not worse than anything else. 27 to the 2x plus 6 greater than or equal to 81 to the x minus 5. All right, same exact stuff. First things first. Are these bases more than 1? Yeah, okay, we're good on that one. Are the bases the same? No. Now, I can't directly turn one to the other, because 27 raised to no power is 81. That's nice and pretty. So do you recognize these numbers at all? 27 or something like that? Do you still have that list from the last unit with cubes and squares and fourths and things like that? You're still going to need that. So get that out and start hunting for any numbers that involve 27 and 81s or anything with 27s in it. Something's got a 27 in it. Something to a power is 27. I know it. I can feel it. 3 cubed. So I could write this in terms of 3s. Now, could I write 81 in terms of 3s also? Is 3 raised to some power 81? All right. So I'm going to break these down into 3s. So it took a little bit of hunting, but I did find that 3 cubed is 27. And I also found on my little table that 3 to the 4th is 81. So I had to go look for some numbers, but I guarantee you, you're still going to need that table. That table's still going to have lots of numbers buried inside of it. So we can write everything with a base of 3. Problem is that these still have powers raised to powers. So again, when you have a power raised to a power, you multiply your exponents. So this one over on the left, this power was 3. This power was 2x plus 6. And 3 times all of 2x plus 6 is 6x plus 18 there. Same deal on the right. 3 to the 4th raised to the x minus 5 is 3 to the 4 times x minus 5, which is 4x minus 20. 4x minus 20 right there. And now that we've got the bases the same, we can basically ignore them. And the same logic works with the inequalities as it did with the equations. So just ignore the bases, and that means that 6x plus 18 has to be greater than or equal to 4x minus 20. And then like any other inequality, we're just going to move things around and solve. Same logic. Maybe I'll get the x's over here. If you subtract 4x, that would make this 2x. You're trying to get the x by itself, right? So I'll subtract 18. That means 2x greater than or equal to negative 38. And then dividing by 2. But with inequalities, always watch out for multiplying and dividing by a negative, right? If you multiply or divide by a negative, you got to flip it. But we're dividing by a positive, so we don't have to worry about that. So when you divide by 2, you get x is greater than or equal to negative 19. And that's the correct answer. And that's fine. The online system might be fine with that. I always want you to put things in interval notation. So that literally means all the x's are from negative 19 to infinity, right? So my answer I'd like you to see is negative 19 to infinity. And bracket on the negative 19 because it can equal negative 19. Questions over that? Okay. So inequalities, you're just basically doing the exact same thing. Of course, the only difference is that you're going to get out a range of numbers instead of just a number. All right, let's see if you can do it. Try this one out. 125. Look on your table. I bet you that's on your table somewhere. 25. Ooh, numbers pop into my mind when I hear 25. Get their bases to be the same. Can anybody find a base that goes into 125 and 25? 5, yeah, okay, write them in terms of 5s. Yep, you're on the right track. Write the 125 as 5 to a power. Same with the 25. And then you're off and running. After you recognize that things are 5 raised to powers, you should write them as such. 125 was 5 cubed. 25 was 5 squared. And of course, when you have powers raised to other powers, make sure you multiply them together. So 3 times all of x plus 2 is 3x plus 6. And 2 times all of 4x minus 7 is 8x minus 14. And once you got the bases the same, you just ignore them. They're gone now. Now these exponents are compared. And you just move a couple things around, divide. Now, in my work, you might have done it slightly different, but in my work, I divide by a negative. So I had to make sure to flip the inequality. So in the end, I got x is greater than or equal to 4. You should have got that some way, somehow. Any questions over how to get that? All right. That's pretty much it. Not that bad, right? Although we must remember the old rules from back in the day, exponent rules. So make sure you understand those. They have to be the same. If your fraction's less than 1, flip it and negate the exponent. And that's about it. So tomorrow's a work day, and we'll do 7.2, 7.1 due today.